As we've been exploring rotations here, on more than one occasion I've mentioned that we need to take a little more care if we have an object that's tumbling. And to do that, we have to extend our definitions of angular variables to be represented as vectors rather than scalars, which we've been doing so far. Now, just to get it out of the way for the pedants among you, technically these are pseudo-vectors and not vectors, but that's a difference that matters to a mathematician. For us, that's nothing that matters. But anyway, I will just start out by kind of doing the most straightforward. Let's think about angular displacement. So first question I want to ask is, can we assign a vector to represent angular displacement? So go ahead, think about it pause the video, think about it for a bit and get back with me. Okay, so to figure out whether we can assign a vector to represent angular displacement or not, I've asked for a little bit of help from a friend of mine. So Snoopy here has agreed to help us figure out whether angular displacement can be represented as a vector or not. If it can be represented as a vector, we know that vector addition commutes, so it would have to be the case that two successive rotations would commute as well. In other words, it wouldn't matter which order I do two particular rotations in. So first, I'm going to rotate Snoopy about the horizontal axis toward the back like this, and then I'm going to rotate him around the vertical axis like this. So let's see what happens. First around the horizontal axis, then around the vertical axis, and we see that he's hanging out like that. All right, now let's go ahead and reverse the order of the operations and see if Snoopy ends up in the same place. So now we'll go ahead and rotate him about the vertical axis, and then we'll rotate him toward the back around the horizontal axis. And we see that he doesn't end up in the same place. So that means that angular displacements do not commute. And this is actually a good thing, because otherwise you'd be unable to parallel park. So thank you, Snoopy, for helping us to figure out that angular displacements don't commute, and therefore we cannot represent angular displacement with a vector. Okay, and so we've seen that because angular rotations do not commute, we cannot represent angular displacements with vectors. However, it does turn out that we can use vectors to represent angular velocities. And in this next clip here, I'm going to ask you to figure out a way that we can assign an arrow, assign a vector. This is IGN. To represent angular velocity. So omega, but now we're going to put a little vector sign over it. So go ahead and get back with me after this clip. So it turns out that we can represent angular velocity with a vector. And so the game that I would like you to play for just a second is, let's imagine that we've got our frisbee and it's rotating like this. What I would like you to do is figure out how you could assign an arrow to that rotation. such that if you passed the arrow to somebody else, they would be able to set up the frisbee spinning the same way. So go ahead and pause the video, and when you've got an answer, come back to me. Okay, so I'm guessing that a lot of you probably tried to do something like put the arrow tangent to the rim like so. And you'd think that this would be okay. But the problem is that someone might decide that it actually looks like that. Or they might decide that the spinning is looking like that. So it turns out that what you have to realize is that the only part that isn't moving when something is spinning is the rotation axis. Now the thing is, you're still left with two choices. You could either assign it to go this way, or you could assign it to go that way. And all that matters is that everybody agrees on the choice. Now, it's taken a while, but the physics community has agreed on a choice. And for the example I was doing, where it's rotating like this, we want the arrow to point this way. The rule for this is one version of the right-hand rule. I like to call this version the hitchhiker rule. You take the fingers of your right hand and you curl it to follow the direction, and then the angular velocity vector points along the axis in the direction of your thumb. And you have to use your right hand. If you use your left hand, you get the opposite answer. So it's a convention, but everybody has agreed to use their right hand for figuring these things out. So say if it was spinning like this, we would go ahead, curl our fingers like so, thumb points up, so we'd have the angular velocity vector pointing up. If it was spinning the other way, we would curl our fingers like this and see that our thumb points down, and so the angular velocity vector points down. All right, and so we've seen that the standard solution for this is when you have an object that's rotating, like the frisbee that we were looking at. If it's rotating like this, we say that the angular velocity would point up, following the hitchhiker rule that I was showing a little bit earlier. And similarly, if it were rotating the other way, like so, we would assign our angular velocity vector to point down. Okay. And it turns that you can show that absolutely everything works the way you expect it should. And it turns out that the definition of angular acceleration is exactly what you think it is. Namely, angular acceleration as a vector is the time derivative of the angular velocity vector. So just a quick reminder, when we're doing this as vectors, so what this means is that the x component of the angular acceleration vector will be equal to the time derivative of the x component of the angular velocity vector, and similarly for the y and z components. So a reasonable question to ask, and so it's one that I'm going to ask you, is will it always be the case that the angular acceleration vector will at least point along the rotation axis? So go ahead and pause the video and get back with me on that. Okay, turns out the answer is no, as you can see in this clip here. What you just saw was a frisbee that was having a bit of a wobble motion. So at one point, the frisbee was doing something like this. And so its angular velocity vector looked like that, call that omega 1. And then at some later point, it was, say, doing something like this. And that didn't turn out too good. Let's try that again. There, that'll have to do. And so omega 2 pointed something like that. So from the chain, so we can say that the change in omega should be equal to the angular acceleration times the change in time, or technically the average angular acceleration here. We can find this by doing a vector subtraction. So we'll say omega 2 minus omega 1, so we'll add negative omega 1 to it, will give me delta omega pointing that way, which means that over that time interval, on average, the angular acceleration was pointing like that. So it's the same kind of deal as what we've seen before. If the angular acceleration vector points along the angular velocity vector, if it points in the same direction, then we're just simply looking at something speeding up without changing its axis of rotation. If the angular acceleration points anti-parallel to the angular velocity, same deal. It's slowing down without changing the rotation axis. But an angular acceleration component that's perpendicular to the angular velocity vector will result in the angular velocity vector pointing in a different direction. And so you'll get this kind of wobbling motion, which the fancy name for that is precession. And we'll be looking at precession in more detail in a later video. Alrighty, so with that, in the next set of videos, we will go ahead and extend our definition of angular momentum, extend Newton's second law applied to rotations, and then ultimately take a look at conservation of angular momentum and gyroscopic precession. So we'll see you in the next few.